Alright, um, hi, I don't really know how to start an introduction to my videos, but, anyways, yeah, today we are going to be doing another video, the second and final part of my atomic theory, videos. I'm assuming that if you're watching this, you've watched the first video on my channel, and if you haven't yet, I recommend you do, because otherwise you'll be really confused and end up having to look back at it anyways, so, yeah, you should go back and watch it. Let me give a quick recap of what happened in the first video anyways. So, in the last video, we talked about how the famous gold foil experiment by Ernest Rutherford led to the widely known atomic model, and after that, I explained what electron orbitals are and how they fit into different energy shells. And, yeah, there was an electron orbital diagram where I showed how to illustrate the electron orbitals in an atom, including how to configure said diagrams with the nearest noble gas, or noble gas configuration. After that, I went over how electrons can get excited and how they have to always go back down eventually. I'm going to recap that part in particular because I'm going to be going over that real quick. Shown here is an example of a calcium atom being excited. One second. The electron is excited, okay, has energy put into it, maybe it's lit on fire or something. So, the electron jumps up in extra orbital. In this case, it jumps from the 4s orbital to the 4p orbital. Okay. In this case, there's enough energy for it to go above the 3d orbital up to the 4p orbital. And you must remember that since orbitals are quantized, you can't be in between two orbitals. There has to be enough energy to cross the gap due to the quantized orbital levels. This is called excitation. The atom is excited, so the electron ascends orbitals. The problem is, though, atoms do not like having an electron away from its orbital because it's unstable, okay? So the atom immediately tries to bring this electron back to its stable, unexcited energy level, okay? So in this case, that would be 4s. The electron goes back to its original orbital, okay? When this happens, the electron loses the energy, okay? And since the electron went 2 orbitals up, it will go 2 orbitals down. So it emits, when it goes down, the energy required to descend those 2 orbitals again. So falling from this orbital to this orbital requires the exact same quantized amount of energy that it took to ascend the orbitals when excited. Now, when this energy is released from the electron going back to its orbital, sorry, by the way, when an electron goes back to its orbital, it is called atom emission, because it is emitting the energy that it used to go up the orbitals in the first place. So this is atomic emission, okay? And when it emits the energy, it is released in the form of light, okay? Now each energy change corresponds to a different color of light, okay? And let me think. I don't know if this can be that well presented considering that it's in black and white, but here is a hydrogen emission spectrum, okay? I don't really know if you can see it that well, but the colors going from right to left are red, blue, dark blue, and purple. Let me see, do I have any colors that match those? Let me see. I'll use here. For example, here is a hydrogen emission spectrum that my teacher printed out for us to refer to. Now you see, it's printed in black and white, but I colored in the dashes that are required for you to understand. So you can see it is measured in nanometers, and it goes from right to left, okay? So it's the largest wavelengths are on the right, and they get smaller as you go left. And the colors are in red, as you can see, red, blue, dark blue, and purple, okay? I don't know if you can read it that well, I think I colored over it, but it says that this is 656 nanometers. The blue is 486, the dark blue is 434, and the purple is 416. Okay, so you can see the wavelengths get smaller as the color changes. Now, as you all should know, every element has a different atomic number, which is the number of protons in the nucleus. Okay? That means that the electrons will have a stronger or weaker pull to the nucleus depending on the atomic number of the element. Okay? So for example, hydrogen will have a weaker pull from the nucleus for its electrons than lead. Okay, because lead has more protons to pull the electrons to it. Okay, so this means that the gaps between orbitals vary between different atoms. So you should note that the visible light spectrum is never the same for two elements. Okay, they're like fingerprints. Okay, they're different for every single atom because of the different atomic numbers. Now we're going to be starting the molecular geometry part of this video. Now, you see, I like molecular geometry because it's pretty simple. All you have to do is just it's a pattern. Everything's a pattern with molecular geometry. You know, there's no deliberate questions that you have to solve. You know, it's not that hard. It's pretty fun actually. Anyways, so when atoms bond, they share electrons, right? And these electrons will repel each other due to negative charges. That means that for every amount of electron pairs in a molecule, there is a different molecular geometry. Okay. Now these geometries are show the maximum distance between these electron pairs. Okay. Now Lewis diagrams, which you've done before, I hope, are helpful. Okay, for knowing what a molecule has in it. Okay. But they aren't good for presenting molecular geometry because Lewis diagrams only show 2 dimensions. This is where wedge diagrams come into play. They show whether or not an atom is away or towards the screen, and optionally, it can also have the angles between the atoms. For example, look at this Lewis diagram of CH4 or methane. Okay, you can see that there's one carbon atom with its 4 valence electrons, each bonding with a hydrogen electron. Okay, we know that, but we don't know the angles between the atoms themselves and where they are geometrically in a 3-dimensional space, because there are 3 dimensions, but this is only illustrating 2. Okay, you see what a wedge diagram does is it uses wedges and dashed lines to illustrate whether an atom is facing away or towards you. Okay, here is the same CH4 atom, but in a wedge diagram. The wedge, okay, at the bottom right here, means that the atom is facing towards the person looking at it. Okay, and the dashes means it's facing away, if that makes sense. Okay, so you can imagine how it looks in a 3-dimensional space. The normal lines means that they're on the same plane as the paper. Okay, so they're not facing towards or away from you, they're in between, I guess. My teacher allowed us to use a molecular geometry chart to refer to. Okay, so as you can see, I don't really think it's focusing that well, but it shows how many electron groups there are in the molecule and the electron pair arrangement. Okay, so as you can see, this is a linear atom because it optimizes how much space there is, and there's no other electrons repelling the atoms. And you can see that as you add more and more of electron pairs and atoms, the geometry changes. Okay, and the angles decrease as well. Okay, you can see that at the start it's 180 degrees, and at the bottom, whereas 6 electron groups, it has 90 degrees, and it will only get smaller as you add more lone pairs and more atoms. Okay. As you can see, I also drew the wedge diagrams for each of the molecular geometries on the side, but I think you'll have to memorize that if your teacher doesn't give it to you in the first place. And yeah. You should also note that when drawing a molecule in a wedge structure with lone pairs, you typically won't draw them. Okay, so here is an NH3 molecule. You can see it has, since nitrogen's atomic number is 7, okay, it has 5 valence electrons, and 3 of those electrons are bonding with the hydrogen's electrons, okay? And that means that there is an extra pair of electrons outside, okay? And you don't draw them because you can assume with the unoccupied space and the electron and the atoms staying away from it that it is a lone pair. Yeah, you can draw them, but it's typically not that common, and I don't think your teacher would like that. Yeah.